Do you remember all those crazy talks we had about fame and glory because of the cooler boat? No, neither do I. Now that summer's finally over and I can use important things like fridges, I decided to continue with the cooler boat project. But I realized that having a boat to tow behind a kayak is kind of impractical when you have a real boat and you could just use a cooler box, kind of like those commercial ones you can buy, which use Peltier coolers and some fans to use 12 volts and then keep your drinks cool, but to make it a little bit personalized and a little bit better. So let me show you what I have in mind and how I plan on doing it. Now, the theory doesn't change. It's all based around these little guys, these Peltier coolers. They are cheap, they are inefficient, but if you have a motor running in a boat and you can control how much power these are being given, then you have a perfect system to create a little fridge. And if you have a fridge, which I have a little cooler box, which I never use, but is perfect for chopping up and putting my device inside, then I think I'm going to have a good fridge here, or a good portable fridge on my hands. So what I'm thinking is using a lot of heat sinks, because the thing about Peltier coolers is you need a temperature differential. They can't, if for example the hot side is 100 degrees, then the cold side will be no colder than its max temperature differential, which in the case of most Peltier coolers is about 50 degrees. In that case, if you could keep the hot side pretty cool, let's say for example 30 degrees, that means theoretically the cold side could be minus 20. Won't happen because it would use a lot of power. But let's just realistically say that if we could cool the hot side enough to be cold in its temperature differential range, then we could get a really good cooling effect for the fridge itself. And what I'm thinking here is potentially using some water cooling, because I'm on a boat. You could just put water in some kind of container to circulate, maybe a radiator type of design, or maybe just using air cooling, using a big CPU cooler on the Peltier elements to keep them cool. So let me swing you towards the bench and show you what I have in mind for doing this. Hello, some time has passed, as you may be able to see. Different shirt, my hair's a bit longer, I'm a little bit older, but not so much older. And what I'd like to talk about today is the conclusion of the cooler boat project. Now, this is a project I put my heart and soul into because I really wanted to believe that it would work. There's much evidence to suggest that it shouldn't work because these Peltier elements traditionally are incredibly inefficient, and this is known to me. There are certain things you have to run them at half power, you have to run them at a certain duty cycle, all these type of things, and you have to cool them a lot more than they can cool. In fact, a funny story is a friend of mine, he has a fridge which he bought for his camper type vehicle, and he ran his battery flat by just leaving the thing running, and that's a huge deep cycle marine type battery, and his fridge is only able to cool, like all Peltier elements, to a certain level below the ambient. They don't reach a level like a compressor fridge. They actually have a level just below the ambient temperature because you keep one side cool and the other side gets colder. So the cooler you can keep the hot side, the colder the cool side will get. And this is the fundamental problem I ran into with this project. However, I gave it my all and I built a circuit which I would like to show you now. I want to show you the finished prototype, and I'd be glad if you came along for the ride. However, ultimately I will not be pursuing it anymore because it doesn't make any sense. Buying a bag of ice or using some ice bricks out your freezer is in this case far more effective than being stranded out on the lake or having to lug around a 1000 watt solar panel to power your fridge, when you might as well simply buy some ice. So let me show you what I've done, and I hope you enjoy it because it is very interesting. Ultimately not successful, but it goes in simply things: water cooling, air cooling, tiny fans, and so forth. So let me show you what I've done. Okay, so let me explain what's going on here. In the previous part of this video, I had an idea of using the ATtiny to control both the MOSFET and a little RGB LED ring that you could then show kind of what status the current fridge was operating on. Here are my 3 Peltier devices. I've got 3 of them here. They have been thermally epoxied to this big piece of aluminium or aluminum. Here is another heatsink. This is just stuck on the bottom with a bit of, I don't know, sticky stuff. And here is the circuit. This is a circuit consisting of an ATtiny over here, an ATtiny, a capacitor which just smooths out the potentiometer, a small 5-volt converter taking from the input power, which in this case is 13 volts, to make 5 volts, which powers this little fan here, which cools the MOSFET, which is over here. IRFP 250, something like that, capable of running up to 50 amps, but still needs a heatsink because it has to be force cooled. I've got input power coming in here. This is coming from this variable power supply up here. And what else you can see on here is, excuse me, the output. The output of what you see on the oscilloscope, is one of them, the yellow line, the yellow trace. Excuse me. The yellow trace is the input signal to the MOSFET. That's coming from the ATtiny, and the blue line, channel 2, is connected to a small current transformer which is directly across the lead which leads to the Peltier elements. And one more thing up here, I have a temperature probe. You can see in this room right now it's 21 degrees. So I will be putting this temperature probe onto one of the Peltier elements, any one of them, I guess, and let's see what happens. So on the power supply side, I have it set to 13.4 volts, kind of standard what you'd have in a car / boat battery. I have it set to a current limit of 5.5 amps, and when I turn it on, a couple of things happen. First of all, excuse the noise, that's the power supply because of the pulsing. It struggles a bit. The frequency, the duty cycle is 32%. The volt, this is the signal going into the MOSFET. Here you can see the little LED ring. When I turn that up or down, let me move this light a bit, sorry. There we go. Now it's minimum, and if you watch the current on here, currently it's 45 half an amp, and when I turn it up, you can see on the screen that the duty cycle increases. Now it's 50%, or yeah, about 50%, so maximum, well, maximum is there, that's 75%. That's just the code inside, and you can see that the power supply is now dropped to 10 volts because of current limiting. So let me remove that current limit by giving it more power. There we go, the power's gone back up. So the maximum power we can draw here is 6.5 amps, and the blue line you can see is that the current transformer is now reading that in all this time the current is flowing, and it's across a resistor which is across the current transformer, and therefore you see that voltage drop below because there's actually a voltage being formed across it, and that's how you measure with a current transformer in an oscilloscope. I can't just measure across the MOSFET. So as you see, what is also happening when I run this at about 50%. So let's drop it there to 50%. From our perspective of the rings, you can see that the temperature's already dropped to 14 degrees. Now it's going to 15 degrees. You can see that the current flowing through all three of these is 2.4 amps, and the temperature's dropped quite low. But if I feel the big heatsink, which is connected to the hot side essentially of these three Peltier elements, it's getting very warm already. And the difference is the top is 19 degrees, and the bottom, if I put the temperature probe into the bottom, you can see that it's 32, 33 degrees. So just imagine I'm already just cooling to an ambient temperature, a little bit below ambient. I'm using 32 watts. And herein lies the fundamental problem. If I really wanted to cool a big cooler box, and I turn it up to max, let's say, I'm using 73 watts of power. So a big battery could only last a few hours, a huge battery, and you don't want to use up your battery, which is used for starting your engine on your boat, or lugging around a lot of batteries just to power your fridge, to get a little bit below ambient. And the second problem is that this heatsink below is heating up so fast. So if I now put temperature probe there, you can see we're climbing massively fast. Or said in other ways, I can put the thermocouple in there, and I can use my infrared thermometer over here, and I can see right now at 30 degrees, 32 degrees max. But it's way hotter because this is not a very good indication. So there we go. 47, 48 degrees. And the top is only at 16 degrees. And we're using 70 watts of power. So that it's just not efficient enough. Now, here comes in the water cooling. The original idea of the cooler boat was, of course, to cool the bottom of the boat with the lake water, and therefore you'd always have sufficient cooling to enable the top to be colder, and you have your temperature differential. But look at this now, we are settling in at 17 degrees. That's not much below ambient, and it's actually rising now because the bottom hot side is getting so warm. So as you see, it levels out and it gets hotter and hotter, because it's always, as I said, it's always a differential. And if I touch these, they're just about ambient, but the bottom is so hot now, it's almost too hot to touch. Let me measure that again to see. 52 degrees. There we go. So obviously, I mean, people may be shouting and saying you have to cool it with a fan. That's okay, but I wanted a really good fridge. So what I'm going to do now is show you one thing that is quite interesting. So when I just turn this off and reset up, I'll be back shortly. Alright, so I've changed the setup a bit now. I just want to explain what's going on. Here I have the power supply, still set to the same values. Here I have a stopwatch to show you how fast something cools. Here I have a thermometer, which is pointing to the, it's currently on the middle Peltier cooler, and I've got a bath underneath it with some water, and the water is just being pushed onto the bottom of the plate, which all the three Peltier elements are stuck on, with a aquarium pump. And you can see that the water inside is about ambient. It's about 22 degrees. So that's not so bad. And what I'd like to show you now is, and this of course was the original concept of the cooler boat, that the Peltier elements would be cooled from the bottom and the top would be getting really frosty because the bottom's about, I don't know, 20 degrees. So you can 20 down from ambient, so you're getting about 0 degrees on the devices in ideal conditions. So I'd like to show you now what happens when you have the water bath at, now you see 22 degrees. So let's see how far below ambient, which is 22 degrees in this case, because we're cooling the bottom to the temperature of the water, we can get the devices. So, and how quickly it happens. So what I'm going to do now is start the timer, turn on the power, and let's set the power to max. You can see it's drawing full current. It's drawing 16 amps, 81 watts, so 6.6 amps at 12.2 volts. And it's dropping very, very fast. As you can see, it's already at 10 degrees. 9. So at full power it can cool quite a bit, but you also have to remember that you have the next problem being that you don't have this kind of power in the battery, and you don't have this kind of cooling. And also these small devices, this is very localized. How would you spread this heat over a big area to cool a whole cooler box full of drinks? It would be a slow process, bringing the whole ambient temperature down. The best you could hope for was trying to maintain some type of temperature once you've cooled it down. So it looks like we've settled at 4 degrees Celsius in about 1.5 minutes. So now you saw what the original temperature was of the water when I put the temperature probe in. So let's put the temperature back into the water. And you can see now the water's already risen by 1 degree, because the water coming off the aluminium being filtered, being splashed back down, is a lot warmer already, considering that is being water cooled directly. And this would be perfect. This is what I considered, that we could have some kind of cooling directly on the bottom, and you could maybe make some kind of circulation system where you pump water through, and you would then be able to cool the hot side with water or giant fans or whatever. But I just realized that it wasn't the cooling that was actually the problem. I think I would have found a workaround. It was the fact that I wouldn't have had enough power on something like a boat or a car when you're not driving the whole time. Maybe a car when you're driving, but it's still a lot of power, 81 watts. I mean, these wires get warm. 6 amps is not a trivial amount of power. So as you see now, the bottom is getting warmer and the top's not getting much colder. It's already gone up. So as a final experiment, I'm going to add something to the water, some ice, and let's see how low we can get the temperature, and then I think we can put this whole thing to rest. Here's a beautiful ice bath to cool the pump water down, at least the ice water down, or at least the water down with ice. So we're going to drop the ambient temperature of the hot side way down to see how much we can actually cool the cool side. So first thing first, I'm going to turn on the pump, get that circulating. There we go. And if I give you a temperature reading here, it's still quite warm from the last one, 22 degrees. There we go. The pump is spraying water on the bottom. The top, as you can see, is a balmy 20 degrees. So, nothing left to do but to turn on the power. And off we go. And as you can see, the temperature drops incredibly quickly. We're at full power now, full cooling power. Let's drop it down just a little bit. Put there. So we're sitting at a nice 5 amps. Excuse the noise of the pump splashing through the ice. The bottom, the heatsink, is now 19 degrees. Still feels a bit warm. The water is spraying directly onto the bottom of this hot plate. Alright, let's go full power for a while. There we go. Alright, we've hit 0 degrees. -1 degrees. The plate is 20 degrees. So I think the maximum temperature differential of these Peltier coolers is about 30 degrees difference. So if the top is at 20 degrees, the bottom could potentially or theoretically get up to -10. Let's see if that's really accurate. And also the water spraying directly onto the bottom of this one. Let's try and probe the next one. It's also cool, -4, -5. And this one here is 1 degree, because he gets the least amount of cooling. Let's go back to our center one. -3 degrees. -4. At some point I assume there will be some frost forming on the tips of these cooling elements, and the allure of this, that it can cool drinks, that it can make ice, is so high. But look at what effort I had to go through. 84 watts for 3 tiny elements, 6 amps, 12 volts, and an ice bath. And now it's finally doing something really, really cool. Excuse the pun. No, don't excuse the pun. It's a good pun. So the plate is at 18 degrees. The water bath is obviously still full of ice. As you can see, we're hitting a cozy -6. As you can see, here's some frost forming. I don't know if you can see that. Let's turn this down a bit. I'm just going to change the lens. All in all, it's a lovely experiment, and you can see how alluring the ice and the cooling and the effect is from electricity making such a cold thing without any mechanically moving parts. It is it's a great concept, but unfortunately it doesn't pan out in the real world. And I find this incredibly interesting. I love these shots, this ice making, this creating the different temperature differentials. And right now the plate that I've been cooling is still sitting at 10 degrees. The ice is obviously at 0 degrees, the ice bath. The maximum or the minimum the Peltier cooler got to is -11, and that is very, very impressive. But it was drawing 80 watts of power, and that is a lot of energy to cool something. There are way more efficient ways, like cooling it in a freezer, for example ice packs, and then putting them into a cooler box and keeping it cool that way. So I hope you enjoyed this video. Please stay tuned for the next one, where I'll be doing more drone stuff. And thanks very much for watching. Cheers.